Hello, welcome. In this short video, we will learn how to understand the finite energy nature of a signal. So, we are going to look at finite energy characteristic of a signal. It is consider a signal x of t. So, consider a signal x of t. So, by definition, the signal x of t is said to be of finite energy if its energy E, which is defined as integral minus infinity to plus infinity x of t, absolute value of x of t squared dt. So that is the definition of energy, and if this value is less than infinity, then that is if the energy E equal to integral minus infinity to plus infinity absolute value of x of t squared dt is less than infinity, then x of t is finite energy signal. So in this video, what we will try to understand is, instead of trying to compute the energy of the signal, we can just look at the following property, that is, if x of t is absolutely integrable, that is absolutely integrable. So what does it mean? It basically means that the integral minus infinity to plus infinity absolute value of x of t dt, that is this integral, is less than infinity. So that means if the signal x of t is absolutely integrable, that is absolute value and then integration, that means this integral is less than infinity, then x of t is most likely a finite energy signal. So in this video, the goal is not to relate these two inequalities theoretically, but to actually look at a practical understanding, that is, given a signal, how do we assess or how do we analyze that whether it is finite energy or not. So for example, assume that x of t is equal to e power minus modulus of t. So that is the definition of the signal x of t. So in this case, we can easily verify that both the energy, for example, the energy E for this signal is simply minus infinity to integral minus infinity to plus infinity e power minus 2 times modulus of t dt. We can easily show that this one will be this one is equal to 1. It is simply based on the idea that we can break down this integral as two parts: integral minus infinity to 0 e power plus 2t dt, plus the second integral is from 0 to infinity e power minus 2t dt. So obviously the first integral should be equal to 1 by 2, and the second one is also of course 1 by 2. So the sum is 1. So that means the signal x of t has energy equal to 1. When this is possible because this computation is possible, or this calculation is possible because this definite integral or this integration has a closed form solution. That means this integral is just e power 2t by 2. So and then we apply the limits. So because the signal this integration has closed form solution, we can calculate the energy. Or similarly, we can also look at the integral minus infinity to plus infinity e power minus mod t dt, and we can derive this integral also, and this will be nothing but integral minus infinity to 0 e power t dt plus again integral 0 to infinity e power minus t dt, and then the first integral is obviously 1 and second one is also 1, so the total value is 2, which is less than infinity. So for this signal, both the conditions are satisfied, that is the energy is less than infinity, which is 1, and less than infinity, and the integral minus infinity to plus infinity modulus of x of t dt, that is this integral is equal to 2 and obviously less than infinity, for x of t equal to e power minus mod t. So that means the signal x of t is equal to e power minus mod t is absolutely integrable. So it is most likely, or it is indeed, a finite energy signal. Now the question is, what if we cannot evaluate these integrals? So how do we know whether the signal is of finite energy or not? So for that purpose, we can resort to plotting the signal. So for example, given this signal x of t equal to e power minus mod t, we can just plot the signal and the square of the signal and look at the shape of their signals. That is so in this case, the blue curve, the blue one is basically the signal x of t equal to e power minus mod t, and the red one is e power minus mod t whole square, or e power minus 2 mod t. So clearly we can see that these two signals are of finite duration, that is on the time scale they actually become 0 after certain values. So in other words, the area under these curves are finite values. So in that case, it basically means that the energy is also finite, and that means the signal is of finite energy. So consider a signal x of t that has a structure like minus t power 2n, that is an exponential of negative of an even power of time t. So consider a signal x of t equal to e power minus t power 2n. So basically it's a even power of t. So in this case, the integral minus infinity to plus infinity absolute value of x of t dt. I mean, it may have a closed form solution in terms of gamma functions, but that is not easy to evaluate without a lookup table. We cannot determine the value without a lookup table or some kind of reference. So in this case, its easiest solution is to just plot this function x of t and look at the graph, and we can easily intuitively judge from the graph whether the signal is of finite area or not. So for example, when n is equal to 2, e power minus t square t power 4, so e power minus t power 4, you can clearly see that that's a signal of finite energy. So both x of t and x square of t, they are actually decaying very soon on both sides of the y-axis. So in other words, these signals are of finite, this signal x of t is of finite energy. And if there are any other functions which may not have any kind of closed form solutions even with lookup tables, then they also can be determined, whether they are finite energy or not can be determined by simply looking at the graph of the signal. So to summarize, in this video we have looked at the finite energy characteristic, that is finite energy characteristic of a signal. That is, given a signal x of t, usually we define it as having finite energy if its energy is less than infinity. That means given by the definition integral minus infinity to plus infinity absolute value of x of t squared dt, that is the energy definition of energy, and if this value is less than infinity, the signal is said to be of finite energy. But instead of trying to evaluate this energy value, we can just look at the function itself and see if it is absolutely integrable. Then if this is the case, then signal also can be judged to be of finite energy. So for example, given the signal x of t, we can actually theoretically verify this for this signal. X of t is equal to e power minus mod t. Then we can derive that energy is equal to 1, and the area under the absolute value of the signal, that is this value, is basically equal to 2. That means the signal is indeed absolutely integrable. That means 2 is less than infinity. So that means the signal is of finite energy. But in the case of signals that have more complex structures, so in the case of signals such as x of t equal to e power minus t power 2n, which are more complex, then the integration may not be easy. They may have some closed form solutions, but the integration is not straightforward. So in this case, we can check whether the signal is of finite energy or not by simply plotting the curve for the signal. This may be easy to judge without even plotting, but there are other signals for which we have to look at the plot and judge if they are of finite energy or not. In terms of the Matlab plot for this signal x of t equal to e power minus t power 2n, we can clearly see that they are of finite energy. So this is the curve for e power minus t power 4, and we can clearly see that the area under these curves is of finite value. That means the signals are of that means the signal is of finite energy. Thus, we can use a Matlab plot to intuitively verify whether the signal is of finite energy or not. Thanks for watching.